Hey, welcome back. Hopefully the weekend was refreshing and ready for more. Cut that out. There we go. So I had pushed off homework 3 till tomorrow so that we could have some time to take a look at it, and then today kind of work on whatever sticking points there might be. Anything come up as you were taking a look? Yeah.
First, like one catch motion thing.
Yeah.
It's saying the file, and when I run it in the other one, it's saying that X and Y don't have the same first dimension.
That usually I can take a look because it might be. Actually, yeah. All right. So here's probably what happened. As you run it, so we run this, and now we run.
Yeah, so like that won't run.
Yeah. Oh, this one doesn't run?
No, the one above it.
Oh. Well, like a lot of times we use Y for a lot of the, oh my God. Yeah, we'll just do that. So like T and Y are kind of like variables that we keep reusing. So now if I try to, well, I don't know. This one's kind of running anyway, but. All right, I can take a look. Because it might be that Y is getting overwritten, and then it might be something else. That one, we can fix that one. Anything else coming up? All right, I'll go take a look. We'll figure out what's going on, and then. Yeah, there's sure.
This is like the first one. So this is like what we're doing.
Yeah.
And then it's like, and then
See how it's telling you that it's it's from another file. It's you go back to that's better. Where were now? Where were you? I think the transition. Did you recently?
like I did this last.
Yeah.
But then is it, do you think it's because I
Down. You're 25.
So is it because I
Better. Yeah, like if you run that stuff and then you go back,
Yes.
it'll say that as 25.
Should I change the picture? If I change
Yeah, or as long as you run that save command. If you don't run it twice, because right now we're at T and right now for TX and Y, and you go through row Y.
So if I run this,
Do you have we scroll out? then you won't have to re-click on it. All right, we tracked down the culprit. What happened was, so like in this catch motion, kind of reading and going through, read video, find the gap lines, all this stuff. But we do all this data processing to get those values, we get a graph. And that graph is X and Y data that are both the same length. But then the next thing this reading does is say that T and Y are now going to be this falling tennis ball data set, which has 2,500 time values and 2,500 height, like Y values. And so if you run, and this is both like a feature and a bug of Jupyter. Like if you run things in a different order than like top to bottom, then it runs in whatever order you ran it in. So if I run this and then go back up and save my data, then I don't have 25 data points, I have 2,500 or whatever, or 16 or something. That's where we ran into a problem. Yeah. Okay. Yeah. one way, like if you're limiting the exit by like instead of the time, you can plot instead of doing a plot of t line, you can just plot the line. So scroll back up to your comment here, just delete that t
Yes.
first plot. Since you're not using the time anyway.
Also, another question is, why is this automatically generated again? Why access and this is not?
That one usually does.
Yeah, you can use it for this one either. Yeah, yes. I'm not for sure I say I didn't change anything about it. Yeah. I didn't add accents. Someone like automatically just generate accents.
Why are you buying it? What does that tell you? When you say T on your specific.
This is just the like on.
But those are coefficients.
I know, but I just
Okay. Well, I just want to see like where 1,000 is, so we scroll up and get rid of that T column. I mean, it should work, right? Like it should be, the PDF output should work easily. I don't know. One day maybe I'll like jump in there and make like an easy PDF exporter button in Jupyter.
Again, that doesn't work if you're not running it on the website.
Yep. All right.
18 pages. So sorry for your PAs.
That's all right.
That's why we just print it with it.
All right, so first thing, as I was kind of walking around looking at this like high resolution data, so we have falling tennis ball. Let's make so I got two figures. One is like a bouncing ball, so it's, and this one's just kind of bouncing straight up and down. And then the next one is how fast it's moving at every point. And it's an approximation because it's just taking like nearest neighbors and figuring out what's the slope. The thing that happens to a lot of people is they're trying to find like what is the velocity at exactly this impact point. But at that point, it's kind of nonsense because you have this tennis ball hitting the ground, it's changing shape, and then it changes shape again. Like we have so much data that all these velocities that are kind of making this like vertical line, they're all just nonsense. Like it's not, because it's not doing rigid body tracking anymore. It's just trying to fit, like trying to find this ball even as it's changing shape. So really the values that we want are kind of way down here and way up there. Which really, it's like the peaks. We want the peaks and the valleys of this data signal. So there is a SciPy function called find peaks if you want to try like importing or using something else. You can also do it yourself. Like if I get the max, it'll give me this 4, and if I get the min, it'll give me this negative 4.75 or 5, whatever that is. So you can do it either way. But if you're interested, there's the from scipy.signals import find peak. And again, this is the magic of Python. It's not that Python does everything better, it's just that it does everything. Like no matter, as long as you can kind of figure out like, all right, what am I trying to do? There's probably like some kind of library and function and open source tool that'll do it for us. So in this case, if I know I'm looking for peaks of this function, then I can say like, all right, is there a find peaks? After some Google searching, sure enough, SciPy signals has a find peaks. I can take a look. My hack is usually I skip over all the descriptions straight down to the examples and figure out what's like the simplest example in here. And I could try this, right? And really I want VY. Let's see what this does. Oh, VHR, my bad. If I could keep track of what variables I'm using, but I can't. And it would help to put them both on the same scale. And let's see, where did I put the X's? So here I can see like I found those 3 top peaks, 4, 3, 2 point something. If I want the bottom peaks, really I could just look for the peak of the negative. I could do find peaks of the negative one. And then it flips the whole graph upside down. Then I have those max values like right before impact. So these are like impact peaks. and then, I don't know, release peaks. Now I've got like top, bottom, everything's kind of working out. And if I want what the ratio of those two, I get 3/4, 3/4, 3/4 okay, every time. If you're interested, pretty cool little library. Find Peak, or well, SciPy is a great like set of tools. Then Find Peaks is pretty helpful. All right, so other thing that came up was looking at this like fall drag equation. So if we go back to that part 2 reading, I'm gonna scroll down to where we actually have drag. So here drag is 0, keep coming down. And here we've got like CD 0.47. So I'll grab this one. But like when we say this is my differential equation, that fall drag, it's not a solution. Like it is an exact calculator for current velocity and current acceleration, but it doesn't tell us anything about like what's happening. So this is our equation of motion for this falling ball, but written as a Python function, which is kind of a weird idea that you can take like a math concept, turn it into like a program like this. I always like to check that it works. So if I say fall drag 10 meters at 0 meters per second, then I'm not moving because my current speed is 0, but I have a acceleration of negative 9.8 or 9.81 if we want. And then if I'm moving downwards at negative 2 meters per second, now I'm still accelerating and I'm moving 2 meters per second. If I'm really flying like 200, I'm like entering the atmosphere, then I'm actually slowing down. Like I'm moving negative 200, but drag is causing me to slow down at 600 meters per second squared. It's too fast. All right, I'll go through like the quick, usually it helps to see numerical process like just over and over. Like the more times you see it, the more comfortable you get with it. So the first step for numerical integration is that time is your variable. Like it's whatever you want it to be. So you can make time steps as big or as small, whatever you want to do. With numerical methods, the smaller you make them, the better your solution is. But here we can say that it's anything. So we'll go linspace from 0 to 3 seconds, and let's make it n steps long. So n is, let's say, 51. If I use linspace, then my time step is already defined. I can't define delta t and the number of time steps independently, so I have to say dt is t1 minus t0. I could vary the time steps, like if I think a lot's going to change in the first couple of seconds and then nothing changes after 3 seconds, I could like increase the time step, but here we just have a constant step through time. The state is going to be an array with 2 values in it, 2 columns. One is the height, so I know the height at time 0 is 10, and then the second column is velocity, and I know the velocity at time 0 is 0. So I'm going to say that it's np.zeros of length of t and 2. And then my first state is 10 and 0. And let's do this. We'll go 1. Now that I have one value, I can calculate all the other values based on that first initial condition. And we even have some other like integration methods. You can use whichever one you want. And you know what, let's mix it up. Life is short. Let's do some fun integration. I'll scroll down, go to part 3, and we'll skip over Euler step and just say it's the Euler-Kromer. And I grabbed one integration method from the readings. There's plenty, and then there's even more. Like the readings are just introducing some simple ones that we can kind of read line by line. Main thing here is instead of an Euler step where one time step has a constant slope, here we're gonna have like 2 slopes of like what was the slope from 0 to dt over 2, and then what is the slope from dt over 2 to the end of the time step. But the input, it's always the same input. We need what is the state, what is our right hand side, like our differential equation, and then how big of a time step do we need. So I'll say state of I is going to be Euler-Kromer of state of I minus 1 with our fall drag and a time step of dt. I did it, nothing happened. So let's look at the height. And sure enough, it starts at 10, and then around 1.5 seconds, probably hit the ground, something like that. And then it falls. In this case, it falls through the ground. If you want, you can add something like if if your height is less than or equal to 0, then we could reverse. Like if we happen to go through the ground, then we can reverse it and send it back up with a coefficient of restitution. Then we should get bouncing. Oh, it broke. Got frozen. What happened? Normal tennis ball, you throw it on the floor, it goes through the floor, and then gets stuck there. This definitely happens in like video games, like if you're looking at a new indie game, this kind of stuff happens. Do you know what happened here? Like, do you know how to fix it? I guess that's one. What would we do to fix it? Not sure. Brute force fix is like smaller time steps is always more accurate. So probably increasing the number of time steps would help. Like make DT smaller. Do you know why it's wiggling like this? So the time step was just big enough that it could go through the ground, but it was just small enough that it couldn't get back above the ground. So it was below, because I said, if my height is less than 0, then reverse the speed and reduce it. Reverse and reduce the speed, which is what it did, but it never got back above the ground. So it kept reversing the speed and slowing it down. So every time step it just gets a little bit slower and bounces underground. So what I could also do is say, if it's less than 0, then also set the height to 0, since it can't bounce through the thing. And there probably still need smaller steps, but since it stays on the ground for 1/10 of a second, it's not normal like tennis ball kind of motion. So we can make it bigger. 501. That looks a little better, right? Just increase the number of time steps so it's not like staying on the ground for a whole time step. That's the cool part about like once you have a differential equation and it's like a Python function, you can add lots of other physics that might be difficult to deal with. Like, it's not the end of the world to figure out, like, where did I impact the ground, but then to resolve the problem with a new initial condition, like, this would have been kind of a time-consuming process rather than, like, 3 lines of code to, like, introduce impact on the ground. Anyway, I think that's cool. Pretty powerful. What else, or anything else coming up as you're working through? Is there a difference between lacrosse? My kids were just arguing with me about this yesterday morning, because I said, yeah, universal gravitation, like a marble and a bowling ball will hit the ground at the same time. Like, that can't be right. And I'm like, well, you could try it. Like, what about a baseball bat? And like, it'll hit the ground. It's still the same. Like, if it's dense enough, as long as drag is not a big factor, they hit the ground at the same time. Is there a difference between lacrosse tennis ball hitting the ground? Like, should we be able to measure a difference? You don't think so? I think the default is lacrosse. All right, so lacrosse, tennis ball, right now they're both just calling fall drag, but fall drag has some inputs where I can change drag coefficient, the mass, the radius. Main thing is that mass is, oh, it was tennis ball is default. All right, so mass, so we got to change the mass for a lacrosse ball. So let's do that. I think it was 160 grams, 150 something. Have you seen this? Have we looked at lambda before? Or have you been using it at all? What do you think that one's doing, that lambda? So, like that right-hand side, and this will be like even for like if you're looking at like SciPy integration functions, they need a function. You can't give it numbers and then expect it to like evaluate. Like it needs some way of like, how do I enter the current state and get the derivative of that state? And so that's what that fall drag is like creating. If you give it the state, then it has these default inputs, but if I want to change those default inputs, I still need a function. I can't plug in the state and then give it a different value. So I'd say the state is going to be y, just some dummy variable, and then the mass, I could call it 1 kilogram. And now it's a new function, but it only has one input, which is what I wanted here. And if I wanted to plug it into like SciPy functions, like maybe I need t to be one of the functions, but I'm not going to use it in this. So it is a function of time and state now, but I'm not actually using that time. Like the state is just independent of that. So that's what it's doing here. And now we can compare lacrosse tennis ball. Does it look great? We can make time a little shorter too, right? More time steps. 2,500. I mean, it ran. Why is it taking so long to plot? There we go. So it's small, but there is a slight difference as we like incorporate drag. Probably not measurable. I mean, the bounce, the rebound, we could probably measure that and see what the difference was. Cool. Anything else in the last like 10 seconds? All right, thanks a lot. We'll be back on Wednesday taking a look at project, at least like for the schedule wise.